SANA-WM, Efficient Minute-Scale World Modeling with Hybrid Linear Diffusion Transformer by researchers from NVIDIA.
Right, getting straight into it.
Yeah, we have a strict format for the top of the show. So if you are an AI researcher or an ML engineer, you really need to pay attention to this one. SANA-WM is a 2.6 billion parameter open source world model that, well, it basically changes the entire math on video generation.
It really does.
It synthesizes 1 minute long 720p resolution videos with exact 6 degree of freedom camera control.
Which is incredibly hard to do.
Oh, absolutely. And the headline here, it achieves visual fidelity comparable to those massive closed-source industrial models like Lingbot World or, HY World Play, but it does it with extreme efficiency.
Yeah, the efficiency is the crazy part.
It trained in just 15 days on 64 H100 GPUs using only about 213,000 public video clips. And at inference, it generates a full 60-second video on a single H100 GPU.
And if you look at the distilled variant, it can actually denoise a 1-minute clip on a standard consumer-grade RTX 5090 using NVFP4 quantization in exactly 34 seconds.
Exactly 34 seconds. That's wild.
Right. And this 36x increase in throughput over open source baselines, it isn't just some clever hardware trick. It's driven by 4 radical architectural shifts, starting with how the model mathematically handles a full minute's worth of memory without instantly exploding.
Okay, so that's the 60-second summary for the short form edit. Now, for everyone listening to AI Paper Podcasts, let's actually unpack this. Our mission today is to break down the exact mechanics behind NVIDIA's claims here.
Because there's a lot to dig into.
There is. So let's transition from those raw stats and talk about that memory crisis. We know sequence length is like the absolute enemy of memory, right?
Oh, without a doubt.
A full 60 seconds of 720p video means dealing with astronomical token counts. How is it physically possible to keep track of all that spatial and temporal data without the compute requirements just skyrocketing?
Well, understand the fix, you have to look at the baseline problem, which is standard causal softmax attention.
Yeah.
It scales quadratically. If you're generating video, every single new spatial token has to look back and compute an attention score against every single past token.
Which is a massive matrix.
Exactly. When you hit thousands upon thousands of tokens across a 60-second rollout, it becomes a hard wall. If you rely purely on softmax attention, your memory footprint would be entirely unmanageable for a single GPU. It would, literally melt the VRAM.
Okay, so they can't use standard attention. But if you strip out attention, you lose the ability to maintain long-term structural consistency, right?
Yeah, the video would just drift into chaos.
So what's the workaround that gives them both?
They engineered what they call a hybrid linear diffusion transformer backbone. First, they tackle the raw input size right out of the gate.
By compressing it.
Right. They push the video through a high-compression LTX2 tokenizer that squeezes the spatial and temporal dimensions into a much tighter latent space.
Okay, that makes sense.
But the real structural innovation is in the hybrid layers themselves. SANA-WM actually alternates between 2 entirely different types of processing blocks.
Oh, interesting.
Yeah, they run 15 frame-wise Gated DeltaNet or GDN blocks, and they strategically interleave those with periodic softmax attention blocks. Specifically, they only put the softmax blocks at layers 3, 7, 11, 15, and 19.
Okay, let's unpack this for the listeners because combining recurrent layers with attention isn't entirely new, but this specific ratio is fascinating.
It really is.
Think of it like the GDN blocks are like reading a really dense textbook and just keeping a running compressed summary in your head. Your brain's memory footprint stays constant because you're just updating that one mental summary frame by frame. You aren't memorizing every single word. But the periodic softmax attention blocks, those are like placing a physical sticky note on specific, crucially important pages. You definitely don't do it for every page that would defeat the purpose, but when you need perfectly exact recall of a visual detail from, say, 40 seconds ago, you bypass the mental summary and jump right back to that sticky note.
Honestly, that's a perfect working analogy for what's happening. The softmax attention acts as a highly precise spatial anchor for long-term consistency, while the GDN blocks efficiently evolve the state frame by frame without hoarding memory.
Right.
And if we look under the hood of those GDN blocks, they use a cumulative linear attention mechanism. So instead of building that massive $1 times the pairwise matrix, they compute the outer products of the keys and values and accumulate them into a compact running state matrix.
Wait, I have to challenge the math on that.
Go for it.
If you're taking outer products and summing them step by step, multiplying a recurrent state by a transition matrix over thousands of tokens across a 60-second video, Wouldn't the geometry eventually blow up? You're compounding values continuously. You can't just arbitrarily cap a matrix without completely destroying the informational signal inside it.
You've hit on the exact reason linear attention is notoriously difficult to scale. Unbounded accumulation of spatial tokens absolutely causes spatial explosion.
Right, because the transition matrix scales with the energy of the keys.
Exactly. If the trace of that key energy matrix gets too large, which happens naturally because the trace scales directly with the number of spatial tokens being processed, the transition becomes expansive. The values compound, and the model output effectively just explodes into static.
So how do they mathematically bound the energy without squashing the actual spatial differences between the tokens?
They introduce a crucial operational step called algebraic stabilization.
Algebraic stabilization.
Right. They explicitly scale the key energy by the trace of the normalized keys. So instead of an arbitrary cap, they divide the key energy by the square root of the hidden dimension, multiplied by the number of spatial tokens.
Oh, wow. So by tying the normalization directly to the dynamic size of the token space, they ensure the trace is always mathematically less than or equal to 1.
Precisely, which guarantees the transition matrix norm never exceeds 1. It becomes strictly non-expansive.
That is a highly elegant algebraic fix. It ensures stability over a full minute of recurrent updates without losing the high-frequency detail.
It really is. And there's one more system-level mechanism they deployed to protect the math, which is the halo exchange.
Right, because when you train a massive model on 64 GPUs, you have to shard or split the sequence across different processors.
Exactly. But GDN uses temporal convolutions to understand motion, which mathematically requires context from neighboring frames. Left unaddressed, if a frame sits on the boundary of one GPU, the convolution kernel creates a boundary error because it can't see the adjacent frame on the next GPU.
Right, and those errors would accumulate and degrade the temporal smoothness, so they initiate this halo exchange.
Yeah, each GPU communicates just the overlapping slice, specifically the KO11 of frames required by the convolution kernel size with its adjacent neighbors.
Which adds almost zero overhead.
Very little overhead, but it ensures that the sequence boundaries remain mathematically perfect across the entire cluster.
Okay, so they've completely solved the memory bloat. The model can physically hold 60 seconds of high-resolution video in its head without self-destructing.
Yeah?
But, I mean, simply remembering a scene is totally useless if the spatial geometry falls apart the second the camera moves.
Right, which brings us to the most difficult part of world modeling.
Exactly. Precise 6-degree of freedom camera control. Usually, to get a generative model to perfectly track a 6-to-off pan, tilt, and roll over a full minute, you have to feed it expensive proprietary game engine data.
Yeah, like dumping synthetic renders from Unreal Engine where the camera coordinates are literally coded into the environment.
Right. So here is where it gets really interesting. How are they doing this without relying on massive manual annotation or pristine synthetic data sets?
Well, they attack the geometry problem with two distinct innovations: a dual-branch architecture for the camera conditioning, and a radically robust pipeline for sanitizing wild data.
Let's start with the dual-branch architecture.
Okay, so conditioning a diffusion model on a camera trajectory over a full minute is a delicate balancing act. If you only inject the camera data globally, say, as a single trajectory vector, the model understands the general direction, but it loses all the fine, high-frequency camera shakes and micro-movements.
Right, the video just looks unnaturally smooth or kind of floats disconnected from physics.
Exactly. But if you only inject it locally, frame by frame, the model loses the overall navigational path and drifts. So they literally separate the macro and micro tracking into two separate pathways.
The dual-branch camera control?
Yes. The first branch uses a latent rate UCP unified camera positional encoding. This branch operates entirely within the compressed latent space and captures the global macro trajectory structure. It provides the overarching map,
Telling the model, like, we are panning 180 degrees over the next 10 seconds.
and place.
But wait, because the latent space is temporally compressed by the tokenizer, let's say it has a temporal stride of 4 or 8 multiple raw frames are being squeezed into a single latent representation. Fast camera motion would just become a smeared blur in that latent space.
Exactly. And that temporal compression is why the second branch is absolutely critical. It's the raw frame plucker mixing branch.
Okay, plucker mixing.
Right.
Right.
Instead of operating on the compressed latents, this branch operates on the raw, uncompressed frame timings. It injects dense plucker ray maps directly into the model.
Let's define that for the audience real quick, because plucker coordinates are a very specific geometric tool. Instead of just giving an XYZ coordinate, a plucker coordinate mathematically defines a continuous line, or ray, in 3D space.
Spot on. By injecting these ray maps, the model is essentially handed the exact physical light rays hitting the camera lens for every single raw frame.
Oh, wow.
It restores that fine camera motion inside each temporal stride, effectively de-blurring the motion that the tokenizer tried to compress.
I see. So it's like the difference between knowing you're generally walking north and actually feeling the exact contours of the gravel under your boots. The global latent branch knows the general pan, but the plucker branch mathematically defines the microgeometry.
Exactly, so the motion stays perfectly sharp.
But that brings me back to my pushback on the data. Where are they getting these incredibly precise plucker coordinates? You need sub-millimeter accuracy for this to actually work.
This is where their robust annotation pipeline comes in. And honestly, it's a huge step for open source AI. Instead of using proprietary synthetic data, NVIDIA extracted precise, metric scale 6DoF camera poses from just around 213,000 completely public internet videos.
Wait, just internet videos. But internet videos are chaotic. You've got different aspect ratios. People crop them for TikTok. They apply bizarre digital stabilization filters. The camera intrinsics, like the exact focal length of the lens or the true optical center, are completely unknown and totally inconsistent from clip to clip.
Which is exactly why traditional structure for motion algorithms and standard pose estimators completely fail on random YouTube clips.
Right.
The researchers started with advanced tools like VIPE and Moj2, but they actually had to make a fundamental mathematical change to the bundle adjustment process within VIPE.
Okay, and for those tuning in, bundle adjustment is that optimization step that takes all the track points in a video and tries to calculate the 3D scene geometry and the camera's path simultaneously, right? It minimizes the reprojection error.
Right. And normally, bundle adjustment operates on a strict assumption that a single video clip was shot with one physical camera, meaning it has one consistent set of camera intrinsics.
Which is a perfectly fair assumption for raw footage from a drone.
Exactly. But it's a terrible assumption for edited internet video. If a creator adds a digital zoom effect halfway through a clip, the apparent focal length changes. If the traditional algorithm assumes the lens is fixed, that digital zoom causes the math to break. The solver thinks the camera just physically accelerated forward at impossible speeds.
Right, the reprojection error skyrockets and the whole trajectory is ruined.
So NVIDIA modified the optimization to treat camera intrinsics, specifically the focal lengths and the principal centers, as completely independent variables per frame.
Per frame?
Yes. Every single frame is allowed to have its own unique intrinsic variables during the optimization process.
Oh, wow. So by making the intrinsics flexible per frame, they essentially isolate and remove the digital noise. They mathematically sanitize the chaos.
Exactly. And that unlocks millions of hours of messy, unstructured internet video to be used as high-precision training data. They turn noise into metric scale ground truth.
That's incredible. Okay, so the model has the hybrid memory to hold the minute-long scene. It has the dual branch geometry to control the camera, and it trained on mathematically sanitized public data.
Yep.
But what happens when you actually render the video? We are talking about 60 seconds of generated pixels here. Does it actually hold up structurally, and how does it compare to the massive industrial models?
Well, generating a flawless 60-second video in one single pass is incredibly difficult, even with perfect memory. You almost always get slight structural artifacts or general softness to the image by the end of the minute.
Right.
That brings us to the third core design, the two-stage visual refinement. SaniWM utilizes a dedicated long video refiner.
How does that refiner actually sharpen the output under the hood?
It uses a technique called truncated sigma flow matching.
Okay, let's pause on flow matching for a second, because standard diffusion removes noise step by step over a very long curved trajectory, like hundreds of tiny Markov chain steps. But flow matching learns an ordinary differential equation. It draws a straight vector line between the noise and the clean image, which is much faster.
Exactly. It regresses a continuous vector field. And by truncating it, they aren't starting from pure static noise. Mathematically, they take the raw stage 1 output video, which has the correct geometry, but maybe some artifacts, and they add a very specific limited amount of Gaussian noise to it. This partially noised state is the starting point. Then, the flow matching model predicts the velocity vector that interpolates between this partially noised state and a perfectly clean, high-fidelity target.
It's like doing a rough charcoal sketch. First, to make sure all the proportions and the 6DoF camera angles are structurally found, and then doing a highly precise second pass with ink to sharpen all the lines and textures.
Precisely. And the benchmark results show exactly why this two-stage approach works.
Yeah.
The authors couldn't just use standard benchmarks like UCF 101 because those aren't designed for minute-long camera-controlled rollouts.
Right.
So they built a highly specific 1-minute benchmark containing 80 scenes across 4 distinct categories: game, indoor city, and nature.
And I noticed in the paper they specifically split these into simple and hard trajectories. The simple ones are your standard S-curves, or panning slowly around a static room, but the hard trajectories are brutal. Massive whip pans, spiral staircases, and double loops where the camera looks around, explores a space, and then has to actively cross its own path. I really want to highlight the hard numbers here because this is where the architectural efficiency shows its teeth.
Let's hit them.
In terms of sheer camera accuracy on those hard paths, Sonono WM beats Lingbot World, it beats HY World Play, and it beats Matrix Game 3.1. It achieves an incredibly low rotation error of just 4.50 degrees over a full 60 seconds.
Which is unprecedented precision for an open source model running on a single GPU.
It really is. But the metric that truly blew my mind is the temporal degradation metric, the delta IQ.
Yeah.
This measures the image quality assessment, essentially how much the structural integrity falls apart from the first 10 seconds of the video to the last 10 seconds. In autoregressive or standard recurrent models, errors compound. When you look at a massive model like HY World Play, by the end of a 60-second video, the quality just completely collapses. It registers a delta IQ degradation of 23.59. The video basically melts into a blurry, hallucinated mess. But SanaWM's truncated flow matching refiner drops that degradation down to just 1.1 Siemens. The physical textures stay crisp the entire time.
And if we connect that lack of degradation back to the geometry, it is what allows the model to achieve true scene persistence.
Object permanence.
Exactly. On those hard trajectories, the benchmark specifically tests for loop closures. If you pan the camera out of a room, look at a hallway for 50 seconds, and then turn the camera back around, does the room still exist, and does it look the exact same?
Usually the model just hallucinates a completely new room or, blurs the background into generic wallpaper.
Exactly. But SanaWM scores 14.8 EGOB on the revisit PSNR metric. It actually remembers the room. It maintains the exact spatial layout and the identity of the objects within it.
So bringing this all together for the listener, what does this all mean for you, the machine learning engineer or researcher listening right now? Why does this specific combination of architectures actually matter to your day-to-day work?
It matters because SanaWM fundamentally democratizes minute-scale generative simulation. Think about the massive hardware requirements we historically associate with this level of 6-to-F temporal persistence. To get a 60-second 720p coherent video with exact camera control, you'd normally need a massive multi-node cluster just for inference. But here, the entire pipeline, whether you are using the bidirectional generator for high-quality offline synthesis or the chunk causal autoregressive generator for streaming it, all fits into a peak memory footprint of just 74.7 GeV.
Which means the entire pipeline fits on a single 80 GeV H100 GPU.
Exactly. It reaches a throughput of 22 videos per hour on that single piece of hardware. And if you use the distilled variant with NVFP4 quantization, you can denoise a full minute of high-definition video in 34 seconds on a standard consumer-grade RTX 5090.
Wow.
That is a paradigm shift. It means small academic labs, independent AI researchers, and lean startups can now actually experiment with, iterate on, and deploy 720p generative physical simulation without needing tens of millions of dollars in compute infrastructure.
When we started this deep dive, we talked about fundamentally changing the math on video generation. SanaWM proves that you don't need to hold the entire uncompressed history of a simulated world in your active memory to maintain a highly accurate, structurally consistent reality.
No, you don't.
You just need a mathematically stable way to take notes like the GDN blocks with algebraic stabilization, and a smarter way to extract precise geometry from the chaotic noise of the internet.
Exactly. And I want to leave you with a final, broader implication to mull over.
Go for it.
If a relatively compact 2.6 billion parameter model can simulate highly accurate 6-degree freedom physical spaces for a full minute on a single consumer GPU just by cleverly combining recurrent states, pluck array maps, and distilled public data, what is stopping us from applying these exact same mathematical efficiency principles to real-world applications?
Oh, that's a great point.
Imagine this pipeline adapted for real-time robotics planning, allowing a drone to simulate 100 possible 60-second futures in real time. Or imagine this integrated into on-device VR rendering engines. We are rapidly approaching a threshold where generative physical simulation requires less compute and runs faster than rendering traditional polygon graphics.
Wow.
What happens to our digital interfaces when the simulation can run faster than reality itself?
Now that is a deep rabbit hole to explore on your own. But that's all the time we have for today's deep dive into the source material. Go read the SANA-WM paper, dive into their open source GitHub repository to see the math for yourself, and we will catch you in the next one.